Hello friends, welcome back to NPTEL online certification course on solid water conservation engineering. I am Rajendra Singh, professor in agriculture and food engineering department of IIT Kharagpur. We are in week 5, lecture 22, and the topic today is problems on grassed waterways. Just to remind you of the course content which we are covering this week, in lecture 21, that is previous lecture, we covered grassed waterways. Today in lecture 22, we will use those concepts to design problems on to handle problems on grassed waterways. In lecture 23, we will handle parabolic grassed waterways, and lecture 24 and 25, we will tackle numerical questions asked in GATE examination on various topics that we have covered already. So, let us start with problem number 1, that is a problem on grassed waterways. Problem 1 states, determine the dimensions of a trapezoidal shaped grassed waterway to carry the peak runoff rate of 4 cubic meter per second. The grade of the waterway is 0.3%. Assume permissible flow velocity of 0.9 meter per second and Manning's n is 0.45. So, we have been given a trapezoidal cross section, we have given the peak flow rate, that is 4 cubic meter per second, the grade of waterway is given, permissible flow velocity is identified and Manning's n value is given. So, it is a very standard problem which we saw, that is a typical problem where we know the shape, we know the bed slope, we know the discharge. So, let us talk about the solution. So, let us assume that the trapezoidal channel, the side slope of this trapezoidal channel is 2:1. Let us also assume that bottom width is 2 meters and flow depth is 1 meter. So, these are the assumptions we are making about the cross section of the channel. So, that means that our channel is something like this. This is 2 meters, the flow depth is 1 meter and the side slope is 2:1 on either side. So, this is the cross section we are assuming. So, cross sectional area will be from the for trapezoidal section, area is B plus ZD times D, or BD plus ZD square. So, we know the values of B and D that we have already assumed, and Z value is already assumed. So, putting these values, B equals to 10, Z equals to 2:1 we assumed, D equals to 1, we get the area, cross sectional area is 4 square meters, that is the cross sectional area of the waterway. Similarly, the perimeter of the waterway, perimeter means we know that if this is our depth. So, this is our D, this is Z and this is B. So, basically perimeter means the length which is in contact with the water. So, if we say A, B, C, D, so sum of A B plus B C plus C D, and because we know the all the values of D and the slope value we know and V we know. So, we can easily calculate, and the direct formula is B plus 2 D 1 Z plus Z square root, and because we know the values of B, D and Z, the value of perimeter we can calculate it 6.47 meters. So, hydraulic radius of the waterway R will be A by P, A we have calculated, P we have calculated. So, value of R is 4 by 6.47, 0.62 meters, that is the hydraulic radius. So, once hydraulic radius is known, we can calculate flow velocity by using Manning's equation, V equals to 1 by n R to the power 2 by 3 S to the power half. The value of R we have calculated just now, and S value, that is the grade of the waterway, is already given 3.3%. So, putting the values, n value is given 0.045, R value we have calculated 0.62 and slope is given 0.3%. So, 0.3 by 100, 1 by 2, and the value of velocity comes out to be 885 meter per second, and we have been given the permissible velocity as 0.9 meters. So, because it is less than 0.9 meters, so that means this is acceptable, and the discharge is Q equals to A times V, area we have calculated is 4 square meters, velocity we have calculated is 0.885 meters per second. So, the Q comes out to be 3.54 cubic meter per second, but we have to design a section that could carry 4 cubic meter per second. So, that simply means the design channel does not have sufficient capacity to carry the peak runoff rate. So, that means we have to take another trial value of bottom width, maybe the cross section has to change. So, we are changing bottom width to 2.5 meters and side slope we are keeping the same. Depth also we are keeping the same. So, that means we have to again calculate all the values cross sectional area, and if we calculate it comes out to be 4.5 square meters. Then now perimeter P comes out to be 6.97 meters, hydraulic radius R comes out to be 0.645 meter per second, meters it is only, and velocity when we put in the Vannick's equation all the values, especially the change value is R. So, it is 0.645 now, then it comes out to be 0.91 meter per second, which is very close to 0.9 meter per second, that is the permissible. So, we may take this value, let us say, and then we need to calculate the Q, and when we calculate Q, this time we get a value of 4.09 cubic meter per second, and we were required to design for 4 cubic meter per second. So, that means discharge capacity of waterway which we have designed is about the same as the peak runoff rate. Hence, the selected bottom width 2.5 meters, depth of flow is 1 meter, and side slope of 2:1 can be used for the construction of the grassed waterway. So, this is how we started with the assumption of the cross section, and we calculated and found that the discharge capacity was not sufficient. Then we changed the bottom width and we did a second iteration to get the right value. So, this is how typically we designed a grass waterway. Now, we go to this second problem, which states that calculate the peak runoff rate expected to occur once in 10 years for design of grassed waterway to dispose runoff from a 35 hectare watershed. Other details are given age under. Time of concentration of watershed is 30 minutes. Runoff coefficient of the watershed for the given characteristic is 0.4, and maximum rainfall for 10 years 30 minute storm is 6 centimeters. So, that simply means we have to estimate peak runoff rate, and we know that we have to use rational formula, that is C equals to CIA by 36. So, that simply means the value of C is already given here, this C value is given here, area is given here. Only thing we have to do is estimate I, that is because we have been given that also is given actually, say 6 centimeter for 30-minute storm. So, that means we have to just calculate the value of I and put in this, so that we can get the peak runoff rate. So, that is for bit A. In bit B, using the peak runoff that we have estimated in bit A, determine the mean velocity of flow and flow depth passing through a trapezoidal grassed way with the following details. The side slope is 4:1, bottom is 5 meter, slope of waterway is 2%, assumes roughness coefficient is 0.04. So, once we estimate peak for the given cross sections, we have to calculate the mean velocity of flow and flow depth, basically depth we have to calculate. So, for bit A, time of concentration T c is given at 30 minutes, C is given as 0.4, A is given as 35, and maximum rainfall for 30-minute duration is 6 centimeters. So, obviously, we, as I already mentioned, we have to use Q equals to CIA, where Q is in cubic meter per second, drainage area is in hectares, rainfall intensity for duration equal to time of desired recurrence value in centimeter per hour. So, these units we have to ensure that we are maintaining the desired units. So, the rainfall intensity for use in rational formula will be this is 6 centimeter over 30 minutes. We want intensity, that is centimeter per hour. So, we have to multiply that by 60 minutes. So, that we calculate the intensity as 12 centimeter per hour. So, now we know C, I, A, all the values. So, putting in equation Q peak, C equals to 0.4, I just now we calculated at 12 centimeter per hour, area is given as 35 hectares. So, the Q peak comes out to be 4.67 cubic meter per second. So, this is the discharge for which we have to to find out the depth and the velocity for the given cross section in bit B. Coming to part B, Manning's equation we have to use for determining the velocity of flow. Every time we do the same, the V equals to 1 by n r to the power 2 by 3 s to the power half. So, value of n and s is already given to us. So, n is given as 0.04 and s is given as 2%. So, 0.02 we have to put here, and so we get velocity in terms of r, that is hydraulic radius, as 3.54 r to the power 2 by 3. Now, coming to discharge is Q equals to A V, and Q value we have already estimated as 4.67 cubic meter per second, that is equal to A V. So, if we substitute velocity value from previous equation just in terms of R V calculated in this equation, we get 4.67 times is equal to 3.54 r to the power 2 by 3 times A, or from here we can say A r to the power 3 is 1.32, and from standard equations we know that A equals to B d plus Z d square, and R is A by P, and A is given as B d plus Z d square, and P is B plus 2 d square root of Z square plus 1. So, that is this is the base width, and these are the two side slope length actually up to the water depth d. So, putting A and R in equation 3, that is A times r to the power 2 by 3 is equal to 1 by 32, that is what we got the relations. A r to the power 3 is 1.32. So, we are putting now in terms of B and D. Substituting known values of B we know is 5, Z equals to 4, which is already given. So, if we put the values of B and Z, that is 5 d plus 4 d square, here 5 d plus 4 d square, here 5 plus 2 d 4 square plus 1 to the power 2 by 3 equals to 1.32. And then if we solve equation in equation 4, only d is unknown. So, we solve this by trial and error. So, if we use d equals to 0.5 meters as first guess, the left hand side of the equation comes out to be 1.848, which is greater than 1.32, that is the right hand side, because we started with A r 2 by 3 equal to 1.32. So, right hand side is 1.32 and left hand side we are calculating, it comes out to be 1.848. So, now we change d, reduce d to 0.4, and in this time we get 1.23, which is less than 1.32. So, that means we have to increase d slightly more than from its current value of 0.4, and let us say that in this iteration we put 0.45 and then we get the value of 1.523. So, it is greater than 1.3, that means we have to reduce from 0.45, and now we do 0.42. When we do, we get 1.344, which is still greater than 1.32. So, now we can assume another value of very close to 0.42, that is 0.416, and when we calculate we exactly get the value of 1.3, which is equal to 1.32. So, d equals to 4.16 exactly satisfies the condition we are looking for. So, the depth of flow comes out to be 0.416 meters. So, the final design dimensions are B is already known 5 meters, D we have calculated. We can also say 0.5 meter by adding a flow board of 0.084 meters. So, total depth capital D is 0.5 meters, Z equals to 4.4:1, Q we have calculated as 4.67 and velocity is 0.85. So, this is what the final design is all about. Then we come to problem number 3, and this says an irrigation main channel of a trapezoidal cross section is designed to carry a discharge of 45 cubic. The allowable maximum depth of water is 1.8 meters. The bottom width of the channel is 6 meter, while side slope Z is to be 2. Assuming roughness coefficient to be 0.025, find the bed slope on which the channel needs to be constructed. So, it is a straightforward problem where everything else is given and we have to just find the bed slope. So, here discharge Q is 45 cumex, maximum depth of water D is 1.8 meters, bottom width is 6 meters, side slope is 2, Manning's roughness coefficient is 0.025. So, for a trapezoidal cross section we know A equals to B D plus Z D square. So, we know B, D and Z. So, by putting the values in this equation we get A equal to 17.28 square meters, and from continuity equation the velocity will be Q by A, Q is because Q is known. So, it comes out to be 2.6 meter per second. And so, using Manning's equation V equals to 1 by n r to about 2 by 3 s to the power half, and the weighted perimeter P is 14.05 meters. So, value of r is, because we know A, we know P, it comes out to be 1.323 meters. So, putting the known value in this equation, that is velocity is 2.6, Manning's n is 0.025, r value we calculated is 1.23, we have to only unknown is slope. So, by putting in this equation we get the value of S as 0.006. That means, in order to carry the discharge for the given section, the bed slope that we have to maintain is 0.6%. That is the bed slope we need to maintain. Then next question, that is that problem number 4 states that a steady discharge of 60 cubic meter per second is passing through a trapezoidal irrigation channel with a bottom width of 5 meter, bed slope of 0.1% and Manning's n value of 0.25. Find the conveyance of the channel in cubic meter per second. So, in this case we have to find out the conveyance, that is the difference in this particular problem. So, here we have been given discharge Q equals to 60 cubic, bottom width is 5 meters, bed slope is 0.0001 and Manning's n is 0.025. So, from continuity equation Q equals to A V, or we can put Manning's equation in this equation. So, A 1 by n r to the power 2 by 3 s to the power half, or A r to the power 2 by 3 n s to the power half. Now, here this term A r 2 by 3 by n, this is known as conveyance of the channel section and generally designated by K. So, that means we have to find the conveyance of the channel section K, that simply means we have to find this entire quantity. So, K is Q by S to the power half, Q value is known 60, S value is known. So, by putting these value we get K equals to 6000. So, conveyance of the channel section is 6000 cubic. So, that is the question. So, but the tricky thing is that you should know what is conveyance, that is the trick involved in this problem was what is conveyance. So, we should always remember that this quantity A r to the power 2 by 3 by n is referred to as conveyance of a channel section. So, that is a learning from this particular problem. Now, we go to problem number 5, which says that design the most economical trapezoidal section of a waterway to carry a discharge of 10 cubic meter per second in a bed slope of 1 in 3000. For stability, the side slope is 1.5:1 and the value of Manning's rough n is 0.025. So, but important thing is here that we do not have to design just a channel, but we have to design a most economical trapezoidal section. So, that has a different connotation and we will see what that means actually. So, for solving this problem we need to know the concept of most economical section or best hydraulic section. Both these terms are commonly used, that is most economical section or best hydraulic section. So, in this equation, that is Q equals to 1 by n A r to the power s to the power half, that is in continuity equation. We are in continuity equation along with Manning's equation, when we write A r to the power 2 by 3 is called as section factor, and for uniform flow section factor is from this A A by P to the power 2 by 3, that is R we are writing in terms of A and P. So, thus for a channel for a given N and S, Q will increase with increasing A, but will decrease with increasing P. So, as you can see here, because Q is a function of, or Q is proportional to A times A P 2 by 3 here. So, that simply means Q is directly proportional to A. So, that means A increases, Q increases, and it is indirectly proportional to P, that means P increases, Q decreases. So, this is a typical relation that with increase in cross sectional area, Q increases, but increase in weighted perimeter, Q decreases. So, this is on this concept of economical section is based on. So, thus for a given A and given shape of the channel, there will be a certain ratio of depth to width y by b for which the section factor will be maximum, and such a ratio gives best hydraulic section. So, a channel proportion that yields a minimum weighted perimeter for a given A is referred to as best hydraulic section. A channel proportion that yields a minimum weighted perimeter for a given cross sectional area is referred to as best hydraulic section. And best hydraulic section is also referred as most economical section, because it also yields a minimum excavation. So, a depth to width ratio is such that it requires minimum excavation. So, that is why best hydraulic section and most economical section, these terms are used synonymously or interchangeably. So, if we try to find out for a trapezoidal channel section, A is B d plus Z d square, and or from here we can write B equals to A by D, that is what we are saying, expressing this equation in terms of B. So, A by D minus Z d, because if you take Z here, it is A equals to, we can also write as D B plus Z d. So, that simply means A by D is equal to B plus Z d, or B equals to A by D minus Z d. So, that is what we are writing here. So, this is the equation, and P is of course, we know is B plus 2 d square root of 1 plus Z square. So, putting this value of B from equation number 2 in perimeter, P is equal to A by D minus Z d, that is coming for B, and this term remains the same. So, 2 d 1 plus Z square root of, and for most economical section, P should be minimum, that we have already seen that P should be minimum for a given A. So, dP by dd equal to 0. So, for minima dP by the first derivative is equal to 0, and that is what we are using here. So, dP by dd, if we do that with reference to d, if we differentiate, then we get minus A by d square minus Z plus 2 square root of 1 plus Z square, and this is equal to 0. So, dP by dd equal to 0, that is what we are doing here. And from here, this is again repeat. So, from here to 1 plus Z square is nothing but A by d square plus Z, that is why just these two terms we are taking on the right hand side of the equation. And by putting the value of A, so A is B d, again we are putting in terms of B d and Z d square. So, we get 2 square root of 1 plus Z square equal to B d plus Z d square by d square plus Z, or we can also write B plus 2 Z d by d. So, simply we are cancelling d 1 out, or d plus 1 by Z square equal to B plus 2 Z d equal to. So, this is a important finding which we have to remember. And then combining equation number 3 and 5, that is P equals to B plus 2, this is what 2 d Z 1 plus Z square, this is what the side of the channel side length is. So, putting 2, we get 2 B plus Z d by 2, or by manipulation we get 2 B plus Z d. Thus, the most economical section hydraulic radius may be given using equation 1 and using 7. So, 1 is nothing but B d plus Z d square, and this one is P equals to 2 B plus Z d. From here we get R equals to 2d. So, this is another important finding. So, these are two important findings, that is d square root of 1 plus z square is b plus 2 z d by 2 and r is equal to d by 2. This is because we can now write that the two conditions for the most economical section are half of the top width is equal to side slope distance for a given side slope from equation number 5, because this is what it is said, and second condition is hydraulic radius is half of the depth from equation number 7. So, these are the two important things we are getting here. So, half of the top width. So, here from this equation, this is the top width and half of that is equal to side length, because if you remember, this is trapezoidal section, this is B, this is Z, and if it is if we say this is D, then if we calculate, then this side is nothing but this is B d plus Z d square. So, from here this length, this is D and this is B and this is Z. So, this is Z d. So, the side is square root of Z square d square plus d square or d square root of Z square plus 1. So, this is the what we are talking about. So, that is why perimeter we write B plus 2 times of this. So, here it is saying that this is equal to B plus 2 Z d, which is here the top width here, this is capital T if we talk. So, this is half of that. So, this is one, and hydraulic radius is half of the depth, total depth of the channel depth. So, these are the two important conditions we have obtained for the most economical section, that is half of the top width is equal to side slope distance for a given side slope and hydraulic radius is half of the depth. So, these are the two important conditions. Along with these, we can also find a third condition, where in that condition can be found if z is also a variable. In the previous case, we said that z is a constant. So, now z is also a variable. So, from this continuing with these equations, b equals to 2 d 1 plus z square minus 2 z d or 2 d 1 plus z square minus z. So, this is simple, we are getting when we put the in terms of v, and putting b in equation number 8, that is 1 and 3. So, a equals to b d plus z d square, and that means it is nothing but what we are showing b d, in place of d we are writing this. So, it is 2 d square 1 plus z square square root minus z plus z d square. On simplification, we will get 1 z d square get cancelled. So, d square is 2 square root of 1 plus z square, that is this come minus z. So, this is 2 z d square minus, this was plus. So, now we are only left with 1 minus z, or from here d can be written as a by this term square root of that. So, in p equals to b 2 d 1 plus z d square, now we put again value of b, and this portion remains the same, and we simply take this common. So, we get this. So, a and p we are getting in these two terms now. So, now putting the value of d from 9 into 10, that is from equation a which we have obtained in equation of p. So, p is 2, this is what we obtained, or let me just go back, so that we can really see what exactly equation 9 and equation 10 was. So, equation 9 was here d is equal to a 1 by 2 square root 1 plus z square minus g to the power half, and this is equation number 10, that is 2 d 1 plus z square minus d. So, what we are saying is that we are putting d from here, this portion, in this equation. So, p will be 2 times of this, and of course, whatever is in parenthesis that remains the way it is. So, that is what it is. So, here and then what is remains here in parenthesis. So, by when we try to little bit manipulate 2 a 1 by half, lower portion we are writing 1 by half, and here it is 2 1 plus z square minus z, or we can also, if we put the square of p square is 4 a, that is 4 a, and this is gets cancelled. So, half it would have been 2 square root of 1 plus z square minus z to the power half, but because we are squaring. So, we are getting only 2 1 plus z square minus z. And for most economical side slope or most efficient section, we say that perimeter has to be minimum with reference to z, that is the variable here, z is a variable. So, dp by z equal to 0. So, hence this value will, if we substitute here and apply the condition, then we get z equals to 1 by cube root 3. And then if you put the value of z in equations, and finally we will get b equals to 2 by square root 3 d. So, the third condition for the most economical Trapezoidal section is the bed width is 2 by root 3 of the depth in terms of b and d, that is the relationship between b and d. So, this is the third condition, and that will be the condition that will be used for solving our problem really. So, now in the problem q was 10 qmex, s was 1 by 3000, z was 1.5, n was 0.025. So, velocity is 1 by n r to the power 2 by 3 s to the power half. Putting the values, we get 0.46 d to the power 2 by 3 in terms of d, because what we are writing is r equals to d by 2. This is the relationship which we obtained, and q equals to a v or 10 equals to b d plus 1.5 d square, and then we are writing velocity from here. So, this we get in terms of b d plus 1 plus 5 d square d to the power 2 by 3 is 21.47. Now, we put the third condition, that is b equals to for economical section 2 by cube root 3 by d, and then square root of 3, sorry, not cube root, square root of 3, and by putting these values here and solving, we finally get the value of d equals to 2.2 meters. So, b will be from this relationship, once d is known, b will come out to be 2.45 meters. So, for most economical section, d is 2.2 meters and b equals to 2.54 meters. So, with this we have seen that different kinds of problems can be handled with whatever knowledge, and as you can see that we frequently use certain formulae. For example, the q equals to a v, that is continuity equation, v equals to 1 by n r to the power 2 by 3 s to the power half, that is Manning's equation, and of course, the q equals to C I A by 36, that is rational formula. These three very commonly used, and of course, we have to always remember that hydraulic radius is a by p, and then for given cross section, if you can remember the formula for a and p, otherwise we can always find out from basic trigonometry, and then our life will be easier. We can solve any problem on grassed waterway. Hopefully, if you solve some more problems and practice few more problems, there should not be any issues in designing grassed waterways. Thank you very much.